Good morning, everyone. Today we have Mr. Abner from NTU, and he will be presenting on plug and play analysis tool, which will be explore the machine learning deep learning module. Please join me and give me a warm round of applause to welcome our speaker.
Okay, so good morning, everyone. My name is Abner Den, and today I'm going to share a plug-and-play analysis tool for understanding deep learning models. Okay, so it is today's outline, and first I'll give a brief introduction of myself, and I'm going to talk about the motivation of developing this tool, maybe some past experience in training deep learning models, or some research papers I have read this year. In the next 3 chapters, I'm going to talk about the core concept of this tool. And the first one is to simply analyze some model information. And the next 2 sections are some deeper analysis of the model information. And last, I'll give a simple demo for this tool. Okay, so I'm a first-year PhD student at National Taiwan University, and I'm also a machine learning engineer at Sinopec AI Lab. And for everyone who don't know what is Sinopec, it is a financial holding in Taiwan. And below is my research field, so if you share similar research field or research interest with me, just communicate with me. Okay, so in my past experience, we found some main problems during model training. The first one is that training dynamics is unstable and sensitive to feature preprocessing. For example, a model may perform better when they use standard norm and in min-max norm they may perform worse. And the next one is different structures have the same model can lead to different behaviors. And there are some examples that layer norm may be more suitable in NLP or just tabular data task, and batch norm may be more suitable in CV tasks. And the next one is if we slightly add a regularization term like dropout, it can lead to performance drop. And the last one is the order of modules can also affect the model performance. So if we put linear in front of layer norm or linear in front of ReLU activation, the model may perform totally different. So it is difficult to improve the model performance without understanding the model behaviors. And it is why we need to develop this tool and plot out the model behaviors. And let's talk about some research papers talking about model behaviors. The first one is differential transformer. The authors has plotted these 2 plots, and the first one, the left one is the traditional transformer, and the right one is their work differential transformer. And then found that the answer's attention weight, the 0.031, is so small to the irrelevant context attention weight, and they say that is called the attention noise. And after they use the differential transformer, they found that the answer's attention weight is totally way higher than the irrelevant context attention weight. And why do they found this is they plot out the attention weight, and they have the evidence to show everyone that differential transformer is a better model for building transformer models. And the next one is a more popular paper called Transformer Without Normalization. And the author finds that the output of layer norm highly resembles that of a hyperbolic tangent function. So we can see like this kind of models, layer norm, if it is a normal layer norm and it's just a linear transformation of layer, and but the author found that in some tasks, the layer norm may look like a hyperbolic tangent function. So they proposed a dynamic hyperbolic tangent called DYT as a drop-in replacement for layer norm, and it can also improve the model performance. So since the authors plot out model informations, they find good insights and further publish their top conference paper. And I'm going to also to talk about some existing open source tools. The first one is Weight and Bias. It is a fantastic tool. I use it every day, and it is very useful for capturing loss and some self-defined metrics like accuracy or information coefficient when training models. And it also provides some visualization of gradient and weight during training. But however, we cannot capture distribution of information because it just plot weights and gradients per epoch, and it is, I don't know how to explain it. And TorchLens and TorchVista plot the model structure like what you can see in the research paper, and the information of each module operators in the model. And Kapton focus more on the interpretability of computer vision models using saliency maps. So it is hard to find a tool that properly visualize model activation, weights, gradient, or some model informations. Okay, so since our purpose is to provide a tool that plots model informations and all the tasks are user specific, it may be affected by data, random seed, model structures, or other things. And I'm not going to talk too much about how to further explain and analyze the figures R tool. I'm just going to focus on how this tool can provide and what can we do. Okay, so it is the core. Okay, so what is our tool doing? It is going to get and plot out some model information. So how do we get model informations? We use this by PyTorch hook. And PyTorch hook, it is a lightweight probes that can attach to any PyTorch module like linear, layer norm, ReLU to capture internal information. And it is also the core of our plug and play analysis tool. And this PyTorch hook allows us to capture the input, output weight when during forward pass and capture gradient during backward pass. And it also can track the changes of the module's parameter during training. But we're not going to talk about the third point since we're capturing information in the inference time. Okay, so it is a minimal example of the PyTorch hook in the inference time. We just defined two functions. The first one is the forward hook, and the second one is the backward hook. And we just open two empty dictionaries to put the model information into it with the predefined register forward hook and register for backward hook in the PyTorch and .module. Okay, so this is some visualization methods I provide in my tools. The first one is the activation scatter plot, just like a thing you see in the transformer without normalization paper, to visualize the input and output of the attention module or like linear module. And the second one is the histogram of all model informations like activations, weights, and gradients to visualize the distribution of these weights to see if there are some gradient vanishing or weight explosion something. And the next one is the CKA similarity matrix heat map to visualize the similarity between two models. And it is good for ablation tests. The next one is attention bar plot to find highly similarity token with respect to the query token. And the last one is binary attention heat map to find the core drivers of input features. Okay, so after we have get the activations using PyTorch hook, we can further visualize the activation. So visualize the dynamics after passing the input data through the specific module. We can dive into how different modules and the hyperparameters affect the activations. And below example is the activation scattered through 4 different learning rates. The eta is the learning rate. And we can see it is totally different in different learning rate settings. And the next one, instead of just plotting out the activation scatter, we can also plot out the histogram of activations. So we can see how the learning rate affects the distribution of activations. In the left side of the image, we can see that it is the activation distribution of big learning rate, and the right side is the activation distribution of the small learning rate. And we can see that if we use the too big learning rate and the distribution will seems like a weird distribution, and if we change to a smaller one, it maybe look like normal. And it is better for deep learning training. And also in weights, we can also plot out the histogram. We visualize the weight distribution to check if the weight is highly skewed, exploded, or vanished. And below is an even more exaggerated example of how different learning rates affect the weight distribution of a linear layer. And we can see that if we even more enhance the learning rate to 10, but I know no one used 10 as a learning rate. And you can see that the distribution is broke. And if we turn into a normal learning rate, and we can see that the deep learning is training in a normal type. Okay, and the last one is gradient. Gradient can also be visualized in a histogram. So we can see if the model is learning properly. For example, if the gradients are too small or too large, lead to gradient vanishing or gradient explosion. So let's see what happens if we don't add any normalization in a gradient. We can find that in the first linear layer and the sixth linear layer, the log gradients. Why do I use log gradients? Because all the gradient is vanishing, and if we just we don't use log, and it will be going to be like in a 0, and so I use log to plot it, and so this model is experiencing in a gradient vanishing. Okay, so this is all of a simple analysis of model informations, and next I'm going to talk about some ablation, visualize the ablation test with between models. Okay, so there will be some math equations in the next section, but it's totally fine to use the tool without knowing those maths, unless you are interested in the theoretical background. So I'll roughly go through those equations. Okay, so to know about the model behaviors after substituting or adding layers, there's a scenario if we just like transformer without normalization. We want to know about how do the model perform if we substitute the layer norm with hyperbolic tangent. So we can use a central kernel alignment called a CKA similarity to measure the similarity between two matrices. And in this task, the two matrices may be like some layer activations like that. And so consider two metrics. We can first calculate the intersample similarity of matrix X and Y. It is we need to calculate the intersample similarity because we need to consider that it is invariant to scaling and linear transformations. And then we center the vectors to ensure each feature has 0 mean. Like this, it is just subtract the mean of the matrix. And next, we use HSIC to measure how similar two vectors or matrix represent to the input data. And simply, HSIC directly measures the inner product of two vectors. And so finally, the CKA similarity represents the normalized HSIC. And we can get a similarity value of two matrices. So how do we visualize the CKA similarity? And so since CKA similarity measures the difference between two layers, we can construct a similarity matrix S, and it has shape of M times N. M is the number of layers in the first model, and N is the number of layers in the second model. So each element Sij represents the CKA similarity between the ith layer of the first model and the jth layer of the second model. So we can see in this figure, there are two figures, and each figure is one CKA similarity matrix. And since higher CKA similarity indicates that the representation of two layers are more similar, so we can see that the first two layers are in two models are quite similar, but if we use ReLU and SILU in different models, they will be way more difference in the backside, in the lower side of the model. So we can use this kind of heat map to answer some questions like, does changing the order of modules affect the model performance, or the different activation functions like the right side of the image change the model behavior a lot. Okay. And the last one is the attention visualization. So what is attention? I'm slightly recap this one if someone is not familiar with attention mechanism or something. For each batch, the attention mechanism compute the attention weight A, and the A represents importance of each token in the input sequence with respect to the others. And so why we need to plot out the attention? There are 3 points, and the third one is that transformer models is widely used in almost every field of deep learning. It is important to know new model behavior by plotting out the attention weights. And the second one is that attention mechanism is often considered a black box, making it difficult to understand how the model makes decisions, and it is also difficult to identify the important features or tokens in the input data. And the last one is through the attention visualization, we can gain insights into the model's behavior and understand how it processes the input data. Okay, so this is the first plot we provide. It is a query attention bar plot. So we can answer the question of which token are most important to the selected query token. From the below image, we can know that token 6 has a highest attention score with respect to token 0. Like this, we set the query as a token 0, and the token 6 is has a highest attention value. And so in tabular data, we can say that maybe token 6, the education feature, and token 0, the salary feature, share strong statistical or learned dependency. And in natural language task, we can probably say that token 0 may be a word that called financial, and it's a word that needs context from token 6, and the token 6 is called, maybe it's profit, it's all financial wordings. And the next one is a binary attention heat map. And so we can find the core drivers of input features by plotting out the attention heat map. So by filtering out low attention scores like this, we can set the threshold to 0.1. So the attention value that is lower than the threshold will be transferred to 0, and the higher than threshold will be transferred to 1. So we can highlight only the most significant relationships between tokens. And the significant tokens may be truly influential for the model decision. And so we can also prune redundant or informative features like the value with 0 to decrease model noise and improve the model performance. Okay, so I'm done with the core concept of this tool, and below is some demo part of our tool. So this is a collect notebook of our tool, and sorry, I have put my slides in the markdown, so you can just get it. Yeah, and open the link of the collab notebook. So let's move on to the notebook. Okay, so I'm not going to run it again because this tool is dependent with the PyTorch and some CUDA package, which is very which is very fat. So I'm just showing that how do you use this tool, and I have packaged it with a Python package, so you can just pip install RedBits. And you need to also install GDown because I have provided some pre-trained. I have also provided some pre-trained model checkpoints and data. Okay, so you can just import some useful tools like attention scatter, histograms, plus CKA into the Python script. And this is the download part of the data. So this is so we need to the user need to have the self-defined model and the data, and you can just put inside the registry. Yeah, we can just put the model you want to analyze to put into the registry. Maybe you have several models, like 10 models or 20 models, but you just want to visualize 2 or 1 of them. So you can select your model into the registry, and the registry will know what the model you are going to analyze. And then we are going to run a single batch inference and just use the registry to know which model is going to do this kind of things. So after a single batch inference, we can get the results of the models. And the results may contain model structure, model information, activations, weights, and gradients. So we can print out the model info, and it is just like the unvisualized Torch Vista-like. The information contains which a layer name and their arguments, keyword arguments like hidden dimensions, or if you use bias. Okay, so after collecting the model information, we can start to plot out our model. So this one is the activation scatter. The input will be there are two inputs. One is the layer input and one is the layer output. So we can and since this layer's input is the previous layer's output, we just replace the input to the previous layer's output, and suddenly we can find the activation scatter like this. Okay, and the next one is the histogram. We can also plot out the activations with a histogram, so to see the distribution of the layer. And let's go into the attention plot. And since attention plot has a more complicated dimension, so it is look like there's a 5-dimension attention score, and the first one is the number of batch, and the second one is the batch size. The third one is the number of attention heads, and the last two is the sequence. Yes, it's the sequence length. And so since we are just plotting a 2D heat map, we just focus on the last 2 dimensions, and it's the sequence length times sequence length. So if we want to plot out the heat map or the bar plot of attention weights, we just need to select the attention weights in each batch and in each head. So it looks like this, and we can define our query token. It may be 0 or each token in a sequence length, and the tokens are the remain sequence length to the query token. So we can plot out the query bar plot like this. And also in the attention heat map, we can do same thing. We just pass into the same attention score, and we can dynamically set the threshold to, dynamically set the threshold to 0.1, and if the tokens is all the tokens in the sequence length. Okay, so in the MLP part, we can also visualize the gradients, weights, and activations with histograms and scatter plots like this. Like this, with the same function. And the next one is the CK similarity. Since CK similarity heat map is to visualize the difference between 2 models, so we just need to input 2 models activation into the function so we can get the full CK similarity heat map. Okay, so let's get back to our slides. Okay, so there are some future works about this tool. The first one is to integrate Torch Vista and Torch Lens, as I mentioned before, the model structure visualizing tool to visualize the model structure, and maybe I think it is more convenient for users to analyze with our tools and with the Torch Vista integration. And the second one is to, we want to support various trading tasks and scenarios. Since we are now more focusing on the tabular data, we want to extend the utility to CV language model or even time series model. And the last one is I want to build a web GUI to make it easier to use and easier to visualize. And there are some special things about my boss, my colleagues, and 2 LLMs. They helped me a lot. And thanks for your attention. So if you have any ideas or questions, welcome to contribute or open an issue to this repo. Thank you.